All right, welcome to the IAAI invited speaker session. Today's speaker graduated with his doctorate in computer science from the University of California at San Diego. He went on to co-found Anchovi Labs that provided computer vision and crowdsourcing as a service. They were acquired by Dropbox, where he went on to do computer vision enabling products. And now he's at Orbital Insight, where he's using deep learning and computer vision to understand the Earth at scale. Please welcome Boris Babenko.
All right, thanks a lot for the introduction. So as Michael mentioned, I'm a computer vision engineer at a startup called Orbital Insight. So if we can go to the slides. So our company gets imagery, predominantly satellite imagery, but also other types of aerial imagery and other geospatial data sets from different partners. And we use a combination of computer vision, machine learning, and statistical modeling to track various economic and environmental trends at global scale. So a little bit about the company. We were founded in late 2013. We've gone through a few rounds of fundraising, raised a Series C recently, and we're located in Silicon Valley. So today I'm going to talk a little bit about the remote sensing space in general. I'll give a bunch of examples of the types of problems that we're working on, some technical challenges that we're facing, and some practical kind of engineering lessons that we've learned that I think have been useful. So usually when I think about Orbital and why I'm excited about it, it's because it's at the intersection of two areas that have gone through a lot of rapid progress in the last several years. So probably this audience is familiar with the type of progress that's been happening in artificial intelligence. But the other area that's really exciting is, people call it Space 2.0 or a new space, but it's basically the satellite image industry. So a few things are happening there. First off, rockets are getting a lot cheaper. And thanks to companies like SpaceX, if they're actually able to reliably resend the same rocket over and over again, it's going to continue getting cheaper. Hardware is getting better and cheaper, in part thanks to smartphones, and I'll mention that in a little bit later, how that's impacting this industry. And also, regulation is getting looser. So I had no idea about this before joining Orbital, but it turns out it's only in 1992 that the US government allowed private companies to operate remote sensing satellites to capture and sell imagery. So it really hasn't been that long. And even then, they regulate the resolution of the imagery that you can sell. And it used to be 50 centimeters per pixel, and now it's 25 centimeters per pixel, which is kind of where the state of the art is, at least in the commercial space. Oops. So satellites come in all sorts of shapes and sizes. Traditional remote sensing satellites were pretty large. They're like the size of a truck. They're really expensive. They're expensive to both build, because there's a lot of custom hardware that you have to build. And they're really expensive to send into space because they're heavy. And you can usually fit just one of these on a rocket. And the nice thing about them is that they can capture really high resolution imagery. So we're talking about something like 30 centimeters per pixel. So every pixel is 30 centimeters by 30 centimeters on the ground, which is pretty remarkable if you think about it. These things are like 300 miles away from the ground. And the fact that they're able to capture such high resolution imagery is remarkable. However, because these things are so expensive, there aren't very many of them in space. So typically, the companies that operate these types of satellites will have a constellation of, say, like 5 to 10 satellites. And what this all means is that if you're interested in a particular spot on Earth, you might only get like one image per month in certain cases for certain locations. So if you're interested in tracking kind of things that are changing rapidly, that's usually not good enough. And the thing that's been happening more recently is this revolution of CubeSats or small sats or nanosats. They kind of go by different names. So these things are the size of a shoebox. They're much smaller. They use typically a lot of the kind of commodity hardware that's been developed for smartphones. And so because of all of this, they're a lot cheaper. They're a lot cheaper to build. You can send up dozens at a time in a single launch. And there are companies that operate kind of on the order of like 100 of satellites like this. And what this all means is that you get much better revisit rates. Now, obviously, there's no such thing as free lunch. And so the downside is because the cameras are not as nice, because the lens is not as big, the resolution is a bit worse. So it's something like 3 meters per pixel, which I think is still pretty remarkable considering how far away the camera is from the ground. So one particular example is this company called Planet. They're one of our partners. They're up in San Francisco. So this is a GIF showing their coverage over time, and it kind of loops over starting in 2014. And at this point, they've launched enough satellites to literally have a new picture of the entire planet every single day. So it's a pretty crazy thing if you think about it. So traditionally, this type of imagery was consumed by human analysts, right? The way people analyzed this imagery is that you have people sitting in front of a computer looking at things. And so, for example, the US government hires a lot of analysts to do this. But now, with the amount, like the sheer amount of data that's being sent down, if it's the entire planet at 3-meter resolution, you can imagine how much data that is. It's no longer feasible to do this analysis by hand. So, for example, the director of NGA recently said, if we attempted to manually exploit the imagery we're going to get in the next 20 years, we'd need 8 million analysts. And so, obviously, the point I'm trying to make here is that this sort of necessitates the use of automated analysis and things like computer vision and machine learning, right? And so that we're kind of at the intersection of these two areas trying to do this. So I'll give some examples of the type of products that we're building. So this is our kind of a first mature product, which is retail sales forecasting. So what we're doing here is we look at major retail chains, so stores like Walmart, Home Depot, different restaurants, and so on and so forth, stores that have open-air parking lots, and we count cars in their parking lots. And the idea is that the number of cars in the parking lot kind of correlates to the revenue for that store. Right, and so kind of using that as an example, I wanted to abstract a little bit and describe the typical workflow for most of our products. So we start with like a set of areas of interest, or AOIs. And in this example, the AOIs are obviously the parking lots of these stores. We place an order with our imagery partners. We basically tell them, here are all the locations we're interested in. And every day, whatever imagery they happen to capture of any of those locations, they send over to us. We plug them through our computer vision module. So in this particular case, it's detecting cars. And in this example, we're working with the higher resolution imagery. So this is like 50 centimeters per pixel, because otherwise it's hard to be able to see cars. And the computer vision module, in this case, spits out the locations of all the cars that it detects in these parking lots. That goes into some database. And then the last piece is some kind of final processing that we call it data science, because it's nice and fuzzy. Sometimes we also consume some other domain-specific data. But the types of things that we do in that part is, for example, again, because this is high-resolution imagery, the revisit rates are not great. So if you think about like a chain like Walmart, for a particular Walmart store, we're not going to see it every day. So every single day, we see a random sample of Walmart stores. And so you have to take that and somehow extrapolate the full signal. So that kind of time series analysis is the last piece to the product. And then our customers consume this data either through an API, or we have a web portal for them to look at, where we visualize the data in different ways. So here's an example of what the data looks like. So this is for Chipotle. The blue line shows their stock price, and the purple line shows the numbers that we produce. Now, obviously, our numbers, what we're actually measuring is not their stock price. We're measuring the number of cars in their parking lots, which we hope correlates to the revenue, and the revenue correlates to the stock price. So they're not going to be exactly the same. But you can see a bunch of places where Wall Street kind of gets too optimistic, and we see kind of a continual decline in the number of cars, and then eventually the stock price corrects itself and comes back down. So this kind of data is really useful for example, financial institutions that want to buy or sell Chipotle stock. So the nice thing is once we developed this product, we had this car detector, and there's nothing really specific in it to retail or parking lots. And so we actually ran it over an entire city. And this is a city in China that's going through a lot of urban development. And we realized we can use car counts, especially when you combine it with other data sources, as a proxy for other things like gasoline demand, urban development, population, income, and so forth. So in this GIF, when it loops over, I think it starts in 2009, you can see there's like a little suburb on the right that kind of pops into existence, which is kind of neat. And all this is doing is just looking at the density of cars that are being detected. Another example that we're working on is crude oil inventory. So it turns out people store crude oil in these giant cylindrical containers. And the containers have a floating lid. So as you take oil out of the tank, the lid goes down. If you put oil into the tank, the lid goes up. And based on where the sun is, it casts a shadow, kind of looks like this little crescent-shaped shadow. And based on that, we can figure out how full the tank is. So at this point, we track tens of thousands of tanks worldwide. They're more or less the same worldwide, but they change in size. And so we can kind of get a consistent global measurement of crude oil inventory. Now, in some countries, like in the United States, this is a regulated industry. And so if you're a company and you have crude oil, you have to report to a government agency how much oil you have. So they survey, I think it's either every once a week or twice a week, or sorry, once every 2 weeks. And they make these numbers public. And so the advantage that we have for countries like the US is that we can do this on a daily basis rather than every week. But the really interesting thing is when you go outside of the US in countries where there isn't very much public information. So for example, in China, there's a lot of interest about what's going on with oil in China. And one thing that we quickly realized is you obviously have to know the locations of the tanks in order to measure how much oil is in them. And we started out by purchasing some data set that was available, but we realized it was really incomplete. So we had to figure out how to find all the missing oil tanks. So we actually did this by building a neural net to detect oil tanks first and foremost. And we scanned pretty much the entire world with that system. And just the number of tanks actually tells you something. It tells you the total capacity for a particular region or a particular country, like how much oil can they store. And this changes over time as well because countries do build new tanks. And so in this example with China, it turned out that the sheer capacity was a lot more than anybody thought. And so that actually made the news. So some other examples, a bunch of other vehicles. This is, again, 50-centimeter resolution imagery. So things like trucks, airplanes, rail cars are different things that you can see in measure from space. This is an example of land use. Sometimes people say land cover. And there's technically a distinction, but we don't really follow that. But this is an example of semantic segmentation, as people would call it in computer vision, where for every pixel, we're trying to classify it into one of several categories. And obviously, the set of categories is going to change depending on the application. But the typical things are like buildings, roads, agriculture, things like that. And we can do this with different resolution. So here's an example of a project that we did with this sort of land use system. This is a collaboration. This was a collaboration with the World Resource Institute. They're interested in tracking deforestation. So they're interested in how much forest is being cut down every year. And on top of that, when people do cut down forest, oh, my slides are automatically flipping now. When people do cut down forest, what does it turn into? Do they build a town on top of that? Do they plant trees on top of that? And so in this case, this is land use, but with these custom land use categories: natural forest, planted forest, urban, and water. This is another example of running land use at scale. This was for a project with the World Bank. They're interested in poverty mapping. So we started with them on a project that was looking at Mexico. And so we just ran this kind of out-of-the-box land use classifier that we had over the entire country. This particular map is showing road density. And you can kind of see major metropolitan areas light up. And so they were interested to see if they could find a correlation between these things and poverty or income levels. This is part of the same project, but kind of taking a different approach. Again, looking at Mexico, but instead of going through a proxy signal like Landuse, we actually tried to apologize about the slides flipping. I have to kind of flip them back and forth. We tried to predict directly from the imagery the income levels in an area. And again, doing this at the scale of an entire country. So the advantage to doing this, usually the way this is done is through surveys, through like a census. That's usually pretty expensive to conduct. Countries usually do it every 5 years or every 10 years, whereas we can do this, in theory, you could do this every week if we wanted to. But we can do it at a much more fine-grained temporal scale. And so if you're thinking about policy, you can make adjustments to your policy or to your aid in a much more real-time fashion. Okay, the last example is, this is related to semantic segmentation, but in computer vision we call this instance segmentation, where for every pixel you want to not only figure out what category it belongs to, you actually want to differentiate between different instances of that category. So for example, if you want to count buildings, it's not sufficient to say this pixel is a building. You actually want to say which building it belongs to. So I wanted to spend some time talking about what satellite imagery looks like and how it's different than the typical data sets that people work with in computer vision. So I come from a quote-unquote traditional computer vision background. I was used to working with data sets like Caltech 101 back in the day, or I guess today's equivalents are things like ImageNet or COCO or CFAR. And one kind of obvious difference with satellite imagery is spectral bands. So I was used to working with RGB imagery or sometimes grayscale, and you do see a lot of that in satellite imagery. But there's also other interesting spectral bands. So oftentimes you'll have infrared, different slices of the infrared spectrum, so near infrared, shortwave infrared. Sometimes you see the thermal. And there are a lot of different resolutions as well. I talked about this before. There's different types of satellites, and they capture imagery at different resolutions. Most of the companies that sell imagery will offer different type of, I guess to them it's post-processing, to us it's pre-processing. But they'll offer things like orthorectification. The picture was taken at an angle. They'll rectify it. And things like atmospheric correction to kind of remove effects of haze and lighting. So the nice thing about satellite imagery is there are a lot of knowns. We know the location of the sun, so we know the illumination of the scene. We know the location of the satellite. The imagery is georeferenced, so it's not entirely accurate, but we more or less know where every pixel is on the Earth. Another nice thing is, again, in traditional computer vision data sets, if you want to recognize cats, for example, if the cat is farther away from the camera, it's small in the image. If it's close to the camera, it's large in the image, so you're going to have to deal with the scale variance. And with satellite imagery, that doesn't really happen. Things don't really move closer to the camera, relatively speaking. So the only time you have to care about scale is if the objects that you're looking at kind of naturally vary in size, but it's not as big of an issue. All right, so with that, I'm going to talk about some of the technical challenges that we face. So usually in computer vision, if you look at kind of typical computer vision workflows, almost always the first step that you see is downsampling the image, because there's usually too much resolution. If you want to recognize cats or bananas or airplanes in like internet images, you don't need a very high resolution image. In satellite imagery, that's not at all the case. We don't have that luxury. We're usually trying to see or measure or count things that you can barely make out in the image. All right, so this is an example of what a car looks like in a 50 centimeter resolution image. Very difficult to make out what it is unless you have some context. And just as an example, this is what a car looks like in ImageNet. And this isn't to say that one is harder or one is easier than the other. They're just very different. In the ImageNet case, you have to worry, again, about scale, about viewpoint, and things like that. So just very different types of problems. Another problem that we commonly run into is severe class imbalance. So two examples I'll give are, let's say you want to detect roads. You're doing this semantic segmentation where you want to label every pixel, and one of the classes you're interested in is roads. The roads might be 1 or 2 pixels in width, And so there are very few pixels with that label. And if you train your classifier naively, it'll just learn to never predict roads. Another example is, this often happens with object detection in general, but especially object detection problems where the object of interest is pretty rare. So for example, if you want to detect ships in open water, you'll rarely see any ships. Almost all the labels are going to be negative. So how do you deal with this? So the typical things that you'll see are things like adding weights to the loss function or tweaking the loss function in some fashion. So probably the simplest thing that you can do is specify a weight per class, and you could do something like take the inverse of the class frequency. And some of the deep learning packages actually support this. And this is a screen grab I got from PyTorch. They have this feature built in. Another example is this info gain loss. They had this implemented in Caffe, I think. So in this case, the user actually specifies a weight per class pair. So there might be some categories that you don't want to give as much of a penalty for confusing. If you're doing, I don't know, apples and pears are very similar. So if the classifier gets confused between those two, you don't care as much. And then more recent approaches to this are things like online hard negative mining, where for every mini batch during stochastic gradient descent, you actually subsample the batch to only pick the samples that have a high loss, and you throw away the rest. And then another example of a recent paper is focal loss. It's kind of similar to that idea, but a soft version of that, where they tweak the cross-entropy loss function such that it gives very low weight to examples that are already being classified correctly. And their kind of driving application is detection, object detection. And so the idea is the classifier will quickly learn how to correctly classify like the easy negatives. And at that point, you want to kind of more or less ignore those samples. But instead of having kind of hyperparameters to threshold and explicitly throw things away, they just tweak the loss function to kind of bring it down. So we found that we experimented with a bunch of these different approaches of tweaking the loss function, and we found that it's usually not enough. It's important, but it's not enough. Because what happens when you have like really severe class imbalance is if you're sampling your batches randomly, you'll often end up with an entire batch that has only one label, right? If it's a binary problem, you'll end up with all negatives. So no matter how you tweak the loss function, it's not really going to do anything in that case. And usually this totally throws off the whole optimization. So you kind of have to use a combination of smarter sampling of the batches. So you want to make sure that you're sampling enough of the rare class, or this kind of hard negative situation where you want to make sure you sample the negative examples that you're currently misclassifying. So another set of problems that we deal with have to do with bias. There's a lot of talk about bias in machine learning nowadays, rightfully so. A lot of it is very sensitive and has to do with kind of the ethical implications. In our case, luckily, it's not nearly as sensitive, and it doesn't have anything to do with ethics, but it is still something that can impact our product. So typically, when we're building a product, we're trying to build some computer vision module. We have some benchmark data set. Again, if we're trying to detect cars, we'll usually have some data set where people have clicked on the locations of cars, and we have the ground truth. And if we want to figure out how well the classifier is working, we'll look at the precision and recall curve, for example. And we might say, oh, look, it gets 90% precision, 90% recall. Those are pretty good numbers, so we're happy with it. Unfortunately, that kind of approach hides a lot of the detail. So, for example, suppose that something like 10% of the images in this data set, and in the real distribution as well, have some property that cause the model to systematically undercount cars. So for example, what if it's snowing in those images, and maybe that messes with the brightness of the image, and that kind of throws off the model a little bit. Not catastrophically, but maybe the counts kind of artificially go down by 10% or 5%. This can actually be a problem for us because, again, The data is pretty sparse in some situations when we're dealing with this high resolution imagery, like 50 centimeters per pixel. And so if on some given day we get a random sample and it just so happens that a lot of those images have snow in them, all of a sudden we kind of undercount the cars and we tell our customers, like, look, there were fewer cars at Walmart this week, and that's might not actually be the case. So this is something that we pay a lot of attention to, and so when we benchmark, we have to think about all these things and make sure that we calibrate, if we can, our measurements relative to these different properties. Another example is trying to use temporal information more. So I'm showing a GIF here. This is with planet imagery, so it's 3 meters per pixel, and the output of one of our land use classifiers. In this case, it's just 3 categories: buildings, roads, and I guess the rest of it is like dirt or something, the stuff in blue. And when you look at this, one thing that you might notice is the classes in the classifier outputs kind of flicker a little bit. So in this case, we're just processing every image completely independently of the other images. And if you want to do things like track change over time, that flickering can be an issue. And so we're starting to look into things where we try to kind of use this temporal stack in a more intelligent fashion. So in some ways, this is kind of similar to video, obviously. But in some ways, it's very different because, first off, the timestamps are not uniform. Right? In video, you usually have a frame every so often. In this case, we have no control over the timestamps of the images. And the second issue is that each image is captured by a different instrument. So there could be kind of small but important statistical differences between every single image. The last example I'll give, or actually maybe there's a couple more, but multispectral imagery, kind of coming back to that. This makes the imagery kind of interesting to work with, but one thing that we found is that if you look at a lot of computer vision literature, you will often see that when people are working on some new application, they'll often fine-tune a model from one that was trained on a large kind of generic data set like ImageNet, right, instead of training from scratch. And this makes sense in a lot of cases. Obviously satellite imagery is a little bit different than something like ImageNet, but you could argue that especially the lower levels of the network are pretty generic. They're finding things like colors and edges and things like that, so it might make sense. But the obvious problem is if we have imagery that has near infrared or shortwave infrared or some other set of bands that's not just red, green, and blue, it's no longer obvious how you would leverage a model that was trained on ImageNet. Right? And people have come up with a few different approaches to do this, and we're kind of experimenting with different ways of dealing with this. So finally, I'll talk a little bit about some of the kind of practical engineering lessons that we've learned. Nowadays, especially if you're working in industry with machine learning, but I think even in academia, because the data sets are enormous now, there's a lot of software engineering that goes into building these things. This is a tweet that I like to show. So if you looked at our code base early on, it kind of looked like a mess. This is kind of a caricature, but just to give you an idea, the first thing we worked on was training a car detector, so we had train car detector.py, and then we got a different data set. Maybe it was larger, but the format was a little bit different, and maybe we wanted to change the neural net architecture, and so we had train car detector 2, and then 2.1, and then another engineer joined, and they worked on it, and they had a different way of doing things. And then we went to airplane detection, and there's another script to train an airplane detector. And so if you're not kind of careful about this and deliberate about this, you end up with a bunch of spaghetti code. Even though the libraries for deep learning are really nice nowadays, but they're still fairly low levels, right? So you have to build on top of them. So we found it really useful and important to design things in a very modular way for the whole team at the company. So if you look at our code base Today, you'll see something closer to this. We'll have like a single script. It'll take a bunch of parameters. It'll take the name of the data set and all these things. And then if you look at the actual code, for example, you're giving the script the name of some data set. And we have an API where you give it this name. It knows where to find the data set on AWS on S3. It downloads it for you. It unpacks it. The format is consistent, so it knows how to parse it. And it can spit out the images and the ground truth. There might be different types of models that you want to train. You might want to train an object detector of a certain type. You might want to train semantic segmentation. So you can give it a flag. And again, we have an API that for kind of the typical things that we do, you can get something out of the box. And then maybe you have to pass it the neural net architecture. Again, we have a library of like the common neural net architectures that we use or that people use in academia. And then finally, once you're done training, you want to save this model and you want to give it a name. And again, we have an API where I guess I actually have a bug in this code because I'm not, in the last line, I'm not passing in the model itself. But again, it puts together all the files, all the stuff that's necessary to recreate this model later. So usually there's like a separate file for the neural net architecture. There's a separate file for the neural net weights. There might be some pre-processing options for the imagery. There might be some post-processing options. So for example, if you're doing object detection and you're doing some sort of non-maximal suppression, there are some hyperparameters there for that. So we put all of this together. And again, this automatically goes to S3. And then later on, if you or someone else wants to run this model, either to kind of play around with it or actually write production code for a product with this model, it's just a few lines. They load the model, they give the model name, and this code knows how to load it from S3, unpackage everything. You read in an image, and then the model object has a predict class that has kind of an intuitive API. In this case, it's an object detector, so it gives you the bounding box locations. So we found that it's really important to design things in a modular way. And the thing that I showed so far makes it really easy to kind of quickly try typical things out on new problems. But a lot of times we do want to do some custom things, or we run into a new problem where kind of the existing pieces don't quite fit. And so the design principle that we follow is to make simple things easy and to make complex or custom things possible. So the typical things that we want to customize are things like the neural net architecture. A lot of times we play around with the loss function. And sometimes the data set format or the model format changes. And so when we write these scripts, we'll typically allow you to pass in either just a short name that it tries to look up in some library, or like the Python path of a custom piece of code. Obviously, it has to follow some API, but if it does, it kind of neatly plugs into the rest, and you can reuse all the other stuff very easily. Another big issue, kind of practical issue that we've run into is versioning. So our customers rely on a consistent data stream. And this is a little bit counterintuitive. But let's say that tomorrow we come up with a much better car detector, and we're really excited about it, and we put it into production. That'll actually be really bad for our customers. A lot of our customers are pretty sophisticated technically. They take our data. They take other data sources that they have. Maybe they buy data like some other company that processes Twitter or something like that, and they want to combine them. So they actually train their own machine learning models on top of our data. And if we make any changes, even if we think that they're improving the quality of our data, that could potentially mess with our customers' models. So whenever we do this, we have to be very careful about cutting a new version. And then our customer support team will go out and tell our customers, like, hey, we have this new version. You should try to eventually switch over to that. Right? And so at any given time, we actually have multiple versions of each product running for this reason. So what are the types of things that affect our output, and what do we have to think about when we're thinking about versioning? So obviously, the model itself, like the car detector, which is the architecture, the weights, again, all the pre-processing, post-processing, all of those things, if any of that changes, the output is going to change. For reproducibility, we usually also store what data set was it trained on, what were all the hyperparameters for training, what was the random seed. That's just kind of for reproducibility. That's kind of intuitive. The thing that was less intuitive for me is the input data. So this isn't always applicable. If your customer is supplying their own input data and you're just processing the data for them, then you obviously don't have any control over the input data, so it's not an issue. In our case, our customers don't give us the input data. They just get data from us. We get the input data, which is mostly the imagery, from third-party partners. And so, again, going with the example of counting cars in parking lots, let's say we realize that we're tracking Walmart, and it turns out that we didn't know about 100 Walmart stores, and we just found out, like, or maybe new stores opened or something like that. If we naively plug that into our system, even though the model is exactly the same, again, that could make an impact on the signal. And again, it may very well improve the signal. But because it's making a change, again, we have to be very careful about versioning. So whenever that happens, whenever the model changes, we always cut a new version and notify our customers. And there's quite a bit of engineering that had to go into this. It's surprisingly not trivial to do. There's a really good paper from a bunch of engineers at Google. It talks about a whole bunch of these kinds of issues that you run into, specifically when you're dealing with a machine learning system in production. Things like the types of technical debt that you encounter. All right, so I think that is all I had. I'm happy to answer questions. We are hiring. We're hiring for data scientist roles. We're hiring for computer vision engineering roles. So you can check out our website for that.
If you come to the mic, you can ask questions at the mic. I'll start with a question. So is there any danger of countries or organizations starting to obscure what you're looking at overhead? For instance, you could easily cover those oil tanks. Or in California, a lot of the parking lots are now putting solar panels over them so they obscure the cars underneath.
Yeah, that's a great question. I mean, in the case of the oil tanks, that's possible. It actually turns out to be pretty expensive and kind of a nuisance for them to do that. So they'd really have to care about it to do it. And I think if it gets to the point where they're doing that, that means we're a raging success because the data is making such an impact. In the case of parking lots, it's already the case that a lot of parking lots are underground or it's a garage and we can't see them. We just need to get enough of a sample to be able to extrapolate.
So about your input data, I think the vision imaging is great, but it has some limitations. So for instance, I don't know if your car detector works very well at night. And the point is that there's other data sets that could help. So for instance, commercial radar data of high resolution perhaps could be looked at. Or certainly for ships, there's AIS data that's very high quality and global and so on and can be acquired. Yep. And so I think the data integration is also a key issue here.
Yeah, absolutely. We're always looking at other data sets that will kind of complement what we're doing with imagery. You're absolutely right. Most of these satellites actually they actually design the orbit, that's so-called sun synchronous orbit, so they don't take pictures at night at all. There are special types of satellites that do take nighttime imagery, but they're usually lower resolution. We do only get imagery from a certain time range. I think it's between like 10 a.m. and 2 p.m. or something like that. There are things like synthetic aperture radar, which we're starting to work with for certain applications. That's really nice because they can kind of quote-unquote see through clouds. That's another kind of obvious obstacle that we run into constantly. If it's cloudy, you can't see stuff. But synthetic aperture radar is an active sensor, so it actually penetrates clouds. So yeah, we're definitely looking at sensors like that as well.
Hi, thanks for the talk. I was wondering if you have applications where you'll be looking at things, you know, the subsurface of the Earth. You know, there are a lot of signals you can collect from the satellite, you know, gamma ray and other things that can help you to infer natural resources and things, you know, under the crust.
That's a good question. Currently, no. So this is kind of outside of my expertise. So as I mentioned, we're starting to work with synthetic aperture radar. I don't think it can penetrate very deep, but I know like people use that type of data to analyze soil and things like that, or like it'll penetrate a canopy. But we're just starting to get into that.
All right, so this might be a dumb question for the naive vision processing guy in the room, but my work, we deal a lot with satellite imagery, and we're trying to set up kind of the semantic labeling. And one thing I haven't really gotten my head around is, you gave the example of using like ImageNet to train to recognize cars or a coffee cup or whatever. And when people do that training, right, you give a picture of a whole coffee cup. Scaled down, it's very easy for it to learn. But in exactly your point, right, when you're trying to recognize a car in a huge image where it's just a couple of pixels across,
yeah.
I'm curious what you use from a kind of a training perspective. I mean, do you take small image tiles and teach a network to have a small field of view and then scan across the image? Or what's computationally an approach for dealing with that?
So yeah, I think most kind of traditional computer vision data sets are image classification. So you have one image and you're trying to classify it into one of 1,000 labels, right? So that's what ImageNet is. But there are problems that people study in kind of outside of remote sensing. In computer vision, there are things like semantic segmentation. And I think it's starting to get a little bit more popular. And it's the same kind of problem where you actually want to classify every single pixel in the image. So the types of models that we use are kind of more similar to those. So like, to give kind of one example, people often talk about fully convolutional nets, which is kind of effectively, you can imagine doing a sliding window approach where you slide a window and you say, is this a car, is this a car, is this a car, is this a car? And if you do this naively, it's a lot of redundant computation. But if your neural net doesn't have any fully connected layers, if it's only kind of all convolutional, you can process an entire image in one go, and you'll get an output for, for every pixel. There's a lot of like little details that I'm throwing out there, but I'm happy to talk offline as well.
Awesome. Cool.
If you have any questions, please come up to the mic. So Boris, what's the most surprising thing you've seen that you can talk about in all the imagery you've looked at?
The most surprising thing?
Something you didn't expect. So when you saw it, it was like, oh, that's interesting.
That's a good question. Yeah, I'm not sure. I mean, I was totally new to the entire kind of geospatial data remote sensing universe. I'd never thought about different spectral bands, for example. But yeah, I'm not sure if there was anything like hugely surprising to me.
Hello, I'm curious about the scalability of the work that you're talking about. So when you scan all of China for oil tanks, for example, how many processors, how much time does that actually take to run something like that? And or if you scan the entire Earth, how long would it take you guys to run that?
Yeah, that really depends on the resolution of the imagery. I mean, it's a huge difference. There's some satellites that capture imagery at, say, 15 meters per pixel, and there are others that capture at 0.3 meters per pixel. And it's, per side of pixels, so you square it. So that makes a huge difference in terms of cost. Now, obviously, you can see different things. Luckily, the oil tanks are pretty big, so you can see them in fairly low resolution imagery. So it kind of all depends on that. The other nice thing is that nowadays, you can go to Amazon or Microsoft or Google and spin up a bunch of GPU-enabled machines kind of on demand.
So, I mean, just give a sense, though. So, for example, with the oil tank example, I mean, how many machines do you end up running something like that, and how long does it take? Unfortunately, off the top of my head, I don't remember. And we might want to keep that confidential in any way. Okay. Okay, thanks.
Is this on? Oh, there it goes. Sorry. Yeah. I just had a question about your training data. how do you get your labels? If you're training, for example, a fully convolutional neural network, you need label data, right?
Yeah.
Do you guys just have a team of hand annotators that go through and find the cars, or how do you get the labels?
Yeah, that's a huge issue for us. So that's definitely like a big part of our company is the processes that we use and the tools that we've developed for collecting ground truth data. Some of our applications especially like require like pretty custom things. We did look around for open source tools for marking imagery. And there are things available, but we weren't completely happy. So we actually ended up developing something completely in-house that's very customizable to our use cases. But yeah, we actually have a team in-house that will either mark images in-house, or sometimes we've used third-party companies if we need a huge amount of data. Sometimes we try to get creative about finding open source data that's available. So for example, a lot of municipalities will fly LiDAR or things like that, or they'll have like things mapped out already. We have to be very careful because it's usually not consistent across different cities, and you don't want to have a bias in your data set, ideally, right? So like not all types of cities will do that. But yeah, it's kind of a combination of all of those things, but we do end up having to mark a lot of stuff in-house for ground truth, both for training and for benchmarking.
Any other questions? Going once, twice? All right, thanks, Boris.
All right, thank you.